So we're going to continue talking about the first derivative test. Yesterday we kind of introduced you to it, and we were only working with polynomials because they should be kind of easy so you can get a feel for it. But now we're going to up the ante a little and talk about the other possible functions and show you how it works. Okay? So if you notice, we have absolute value, rational, piecewise, and trig. I'm going to focus on just absolute value for this video, and I'll post videos for each of the other three later, okay? So in order for me to use the first derivative function, I need to find the critical numbers. But I can only find critical numbers on a function that is continuous. It doesn't have to be differentiable, it just has to be continuous. So if you imagine what 9 minus the absolute value of 2x plus 5 looks like, well, I know it's an absolute value graph. So absolute value graphs are continuous for all real numbers. So that means that I can go ahead and find the critical numbers. So the critical number is going to come from getting the derivative and finding where the derivative is 0 or where the derivative would not exist. So we didn't talk about how to find the derivative of an absolute value function because it's an absolute value function. So if you think about what the graph is, I can tell you that it's not differentiable for all real numbers because this graph more or less will look something like this, right? And it's because it has this sharp turn right here at that vertex, that absolute maximum, that it's not differentiable. So the way we're going to kind of work around that is we're going to go ahead and think about the absolute value as a piecewise function, right? So it's made up of two different functions. Specifically, they're made up of two different lines. So the first line could be 9 minus 2x plus 5. And the other one could be 9 plus 2x plus 5. So in essence, that's what I have. But I need to figure out, if I'm going to make it a piecewise function, like where's the switch up occur? So it's going to occur at that maximum. And because I remember the integrated 4 stuff, the parent function, absolute value of x, has a vertex located at 0, 0, right? But I see that this graph has been moved up 9 spaces by this 9 right here. And I'm picturing this 2x minus 5 as, 2 parentheses x plus 2.5. So I see that it has a horizontal compression, and I see that it has a horizontal shift as well. So based off this 2.5 and based off that 9, I know that when x is greater than 2.5, right here is where I got that 2.5. It's going to look like that graph. And the reason I say that is because this right here ensures that I have a negative slope, and that right side of the graph will have a negative slope. And then over here would have to be x less than or equal to 2.5, which means on the left side of the graph, that's where the graph would have a positive slope, hence the positive 2x. So I'm going to take the derivative of each of the parts of the piecewise function to help me with my first derivative test. So because I was able to draw the graph, I know my answer should be that I have a absolute maximum when x is negative 2.5. Oh, snap, that should have been negative 2.5. Oh, it's raining. Sorry about that. So because I have the graph, like the first derivative test is just to make sure I know how to use it, because some of these other ones, it's going to get a little dicey. Okay, so if I take the derivative of the first part right here. Actually, that should be the second part. This will be my first part because this is this left side of the graph right here. Right? It would be 9 plus 2x plus 5, so it would be 2x plus 14. And so the derivative would have to be 2 when x is less than negative 2.5. All right. Same idea, but now I'm going to take a look at the right side of the graph, this one, which is this part of the graph right here. So 9 minus 2x minus 5 would equal negative 2x plus 4. So then f prime would equal a negative 2 when x is greater than negative 2.5. And I have to go back because I did not write this carefully. Equals there, less than or equal to there. As far as I know, which of these had the equal to part shouldn't matter because they're both going to give you the same output either way. So don't fret about that. Okay. So let's put it all together for the first derivative test. I have found where my derivative will, or I've found the critical number. It's right here at this value that I circled in the yellow because that's where my derivative will not be differentiable because that's where I have the sharp turn. So I know I have a critical number at negative 2.5. Oops, wrong eraser. Right, and a lot of this is, well, how would I think about that? And I'm showing you how to think about it. When you have absolute values and you have to find a derivative, think about it as a piecewise function. If you can identify the transformations done to an absolute value function, you should be able to identify that vertex pretty quickly. So I know C would be negative 2.5. So when I draw my number line at negative 2.5, I know my derivative is undefined. Okay. And I have my derivative, which is composed of this piecewise function. So if I choose a number less than negative 2.5, so let's say negative, 5, I replace this x with a negative 5, I'm going to get a positive 2. So I know that my derivative will be positive to the left of negative 2.5. When I choose a number bigger than negative 2.5, so let's say, 0, I replace this x with the 0, my derivative should be a negative 2. So based off that critical number, I know I should have a relative max when x equals negative 2.5. And I would say this is a little more of a complicated problem because of the way that I don't really have nice numbers to work with. My slope wasn't 1. But I would rewatch the video if you're a little lost and ask questions during the office hours if you need to. Good luck. Actually, not done, because to identify the relative extrema, I know at what x value I'm going to get the relative extrema, I need to plug that into my equation to actually get the coordinate point. So if x is equal to negative 2.5, then I need to go ahead and find f of negative 2.5. So I get 9 minus the absolute value of 2 times a negative 2.5 plus 5. So it'd be 9 minus absolute value of 0. So f of negative 2.5 equals 9. And that's where you have your relative maximum. Now that's the actual final answer.